going to stay here for 1.5 hours, should I? I think I'm gonna do the Italian thing first. And I'm going to review Red Black 3 article and Bloom filter. And then the rest of the day, what I'm probably gonna do is use ChatGPT to build all the other articles to review them. I already did the structure of all of them. So I already got the 10 different algorithms I'm gonna do for each one of them. Some I did less, and then some I did a little bit more. I'll make sure that it is streaming. Yeah. I'm gonna do this thing here first, and then I'm gonna start.
Fa,
Fa,
Does.
fisso,
fisso,
Set. Unchanging.
3,
3,
3.
desiderare,
desiderare,
Desire.
aria,
aria,
Air.
bene,
bene,
Well.
anche,
anche,
Also.
giocare,
giocare,
Play.
piccolo,
piccolo,
Small.
fine,
fine,
End.
mettere,
mettere,
Put.
casa,
casa,
Home.
leggere,
leggere,
Read.
mano,
mano,
Hand.
portare,
portare,
Carry.
grande,
grande,
Large.
compitare,
compitare,
Spell. Words.
aggiungere,
aggiungere,
Add.
anche,
anche,
Even. Also.
terra,
terra,
Land.
qui,
qui,
Here.
devo,
devo,
I must.
grande,
grande,
Big.
alto,
alto,
High. Tall.
tale,
tale,
Such.
seguire,
seguire,
Follow.
atto,
atto,
Enact.
perché,
perché,
Why.
chiedere,
chiedere,
Ask.
maschi,
maschi,
Men.
cambiamento,
cambiamento,
A change.
è andato,
è andato,
He. She went.
luce,
luce,
Light.
tipo,
tipo,
Kind. Of thing.
spento,
spento,
Turned off.
bisogno,
bisogno,
Need.
casa,
casa,
House.
immagine,
immagine,
Image.
provare,
provare,
Try.
noi,
noi,
Us.
di nuovo,
di nuovo,
Again.
animale,
animale,
Animal.
punto,
punto,
Point.
madre,
madre,
Mother.
mondo,
mondo,
World.
vicino,
vicino,
Near.
costruire,
costruire,
Build.
se stesso,
se stesso,
Himself.
terra,
terra,
Earth.
padre,
padre.
Father.
I already watched a couple of videos about red black trees, so I kind of know, and I already studied this a little bit. I redid some of these stacks, but I wanted to study. Actually, I did the whole thing already, but I wanna study more before I put this one on the blog. So it's pretty much a kind of tree that is binary, which means that there's up to 2 nodes as children at most. And some of the nodes are going to be red and some of the nodes are going to be black, and that's what maintains the balance of the tree. And every time you insert a node, the algorithm is gonna make sure that there is an equal amount or roughly equal amount of black and red nodes based on the order. I think that every red child should have a black parent or something like that. Some kind of rule like that. And that's the point of the tree. Yeah, the root node must be black. If a node is red, then its parent is black. Yeah. The root node must consider the same number of black nodes. The only thing that I didn't understand about this really well is like if there's anything special, what is the order of the values of the nodes, or if there isn't anything about that. I think I'm gonna probably end up leaving it like this because I don't see anything else to change there. That would make sense. I already changed some of the stacks off stream, and then I left to review a little bit more to see if there's anything that I can change or add here. But this is not that interesting to me because I haven't seen any applications of this. So it's hard to know. I'm contemplating on whether or not leave it like this or even delete this one and not put it there until I encounter something that uses this to put on the blog.
red, black tree. This article may be too technical for most readers to understand. Please help improve it to make it understandable to non-experts, without removing the technical details. January 2023, learn how and when to remove this template message. In computer science, a red, black tree is a kind of self-balancing binary search tree. Each node stores an extra bit representing color, red or black, used to ensure that the tree remains balanced during insertions and deletions. A node is a basic unit of a data structure, such as a linked list or tree data structure. Nodes contain data and also may link to other nodes. When the tree is modified, the new tree is rearranged and repainted to restore the coloring properties that constrain how unbalanced the tree can become in the worst case. The properties are designed such that this rearranging and recoloring can be performed efficiently. The rebalancing is not perfect, but guarantees searching in O, log n, time, where n is the number of entries, or keys, in the tree. The insert and delete operations, along with the tree rearrangement and recoloring, are also performed in O, log n, time. Tracking the color of each node requires only one bit of information per node because there are only two colors. The tree does not contain any other data specific to it being a red, black tree, so its memory footprint is almost identical to that of a classic, uncolored, binary search tree. In some cases, the added bit of information can be stored at no added memory cost. History edit. In 1972, Rudolf Bayer invented a data structure that was a special order 4 case of a B tree. These trees maintained all paths from root to leaf with the same number of nodes, creating perfectly balanced trees. However, they were not binary search trees. Bayer called them a symmetric binary B tree in his paper, and later they became popular as 2, 3, 4 trees or just 2 to 4 trees. In a 1978 paper, A Dichromatic Framework for Balanced Trees, Leonidas J. Gibbs and Robert Sedgwick derived the red, black tree from the symmetric binary B tree. The color red was chosen because it was the best-looking color produced by the color laser printer available to the authors while working at Xerox PARC. Another response from Gibbs states that it was because of the red and black pens available to them to draw the trees. In 1993, Arne Anderson introduced the idea of a right-leaning tree to simplify insert and delete operations. In 1999, Chris Okazaki showed how to make the insert operation purely functional. Its balance function needed to take care of only 4 unbalanced cases and 1 default balanced case. The original algorithm used 8 unbalanced cases, but Corman et al. 2001 reduced that to 6 unbalanced cases. Sedgwick showed that the insert operation can be implemented in just 46 lines of Java code. In 2008, Sedgwick proposed the left-leaning red, black tree, leveraging Anderson's idea that simplified the insert and delete operations. Sedgwick originally allowed nodes whose 2 children are red, making his trees more like 2, 3, 4 trees, but later this restriction was added, making new trees more like 2 to 3 trees. Sedgwick implemented the insert algorithm in just 33 lines, significantly shortening his original 46 lines of code. Terminology edit. A red, black tree is a special type of binary search tree, used in computer science to organize pieces of comparable data, such as text fragments or numbers, as e.g. the numbers in figures 1 and 2. The nodes carrying keys and / or data are frequently called internal nodes, but to make this very specific they are also called non-nil nodes in this article. The leaf nodes of red, black trees, nil in figure 1, do not contain keys or data. These leaves need not be explicit individuals in computer memory. A null pointer can, as in all binary tree data structures, encode the fact that there is no child node at this position in the parent node. Nevertheless, by their position in the tree, these objects are in relation to other nodes that is relevant to the RB structure. It may have parent, sibling, i.e., the other child of the parent, uncle, even nephew node, and may be child but never parent of another node. It is not really necessary to attribute a color to these end-of-path objects, because the condition is nil or black is implied by the condition is nil. See also this remark. Figure 2 shows the conceptually same red, black tree without these nil leaves. To arrive at the same notion of a path, one must notice that example 3, paths run through the node 1, namely a path through 1 left plus 2 added paths through 1 right, namely the paths through 6 left and 6 right. This way, these ends of the paths are also docking points for new nodes to be inserted, fully equivalent to the nil leaves of figure 1. Instead, to save a marginal amount of execution time, these, possibly many, nil leaves may be implemented as pointers to one unique, and black, sentinel node, instead of pointers of value null. As a conclusion, the fact that a child does not exist, is not a true node, does not contain data, can in all occurrences be specified by the very same null pointer or as the very same pointer to a sentinel node. Throughout this article, either choice is called nil node and has the constant value nil. The black depth of a node is defined as the number of black nodes from the root to that node, i.e. the number of black ancestors. The black height of a red, black tree is the number of black nodes in any path from the root to the leaves, which, by requirement 4, is constant. Alternatively, it could be defined as the black depth of any leaf node. The black height of a node is the black height of the subtree rooted by it. In this article, the black height of a nil node shall be set to 0, because its subtree is empty as suggested by figure 2, and its tree height is also 0. Properties edit. In addition to the requirements imposed on a binary search tree, the following must be satisfied by a red, black tree. Every node is either red or black. All nil nodes, figure 1, are considered black. A red node does not have a red child. Every path from a given node to any of its descendant nil nodes goes through the same number of black nodes. Some authors, e.g. Corman and al., claim the root is black as fifth requirement, but not Melhorn and Sanders or Sedgwick and Duane. Since the root can always be changed from red to black, this rule has little effect on analysis. This article also omits it, because it slightly disturbs the recursive algorithms and proofs. As an example, every perfect binary tree that consists only of black nodes is a red, black tree. The read-only operations, such as search or tree traversal, do not affect any of the requirements. In contrast, the modifying operations...
Honestly, I'm not gonna put this stuff. I think I'm gonna wait. Maybe I'll leave like this because it's not worth deleting as well. But I'll probably wait until I find some some application where this is used, so I understand more what is the benefit of using that. But I don't see the point in putting that in the blog if I haven't seen it. I think it's just gonna be for putting more things there. So probably in the future I'll put it there, but now just gonna put these other ones. This one I remember seeing a good article about this, explaining on Ethereum how it works for storing information on the filters. This is new, they changed this. I still don't trust this, obviously, 100%. I'm gonna read all these articles here and then I'll change more. So that is correct.
Bloom filters, introduction and implementation. Suppose you are creating an account on Geekbook. You want to enter a cool username. You entered it and got a message. Username is already taken. You added your birth date along username. Still no luck. Now you have added your university roll number also, still got, username is already taken. It's really frustrating, isn't it? But have you ever thought about how quickly Geekbook checks availability of username by searching millions of username registered with it? There are many ways to do this job. Linear search, bad idea. Binary search, store all username alphabetically and compare entered username with middle one in list. If it matched, then username is taken, otherwise figure out whether entered username will come before or after middle one, and if it will come after, neglect all the usernames before middle one, inclusive. Now search after middle one and repeat this process until you got a match, or search end with no match. Bloom filter is a data structure that can do this job. For understanding Bloom filters, you must know what is hashing. A hash function takes input and outputs a unique identifier of fixed length which is used for identification of input. What is Bloom filter? A Bloom filter is a space-efficient probabilistic data structure that is used to test whether an element is a member of a set. For example, checking availability of username is set membership problem, where the set is the list of all registered username. The price we pay for efficiency is that it is probabilistic in nature. That means there might be some false positive results. False positive means it might tell that given username is already taken, but actually it's not. Interesting properties of Bloom filters. Unlike a standard hash table, a Bloom filter of a fixed size can represent a set with an arbitrarily large number of elements. Adding an element never fails. However, the false positive rate increases steadily as elements are added until all bits in the filter are set to 1, at which point all queries yield a positive result. Bloom filters never generate false negative result, i.e., telling you that a username doesn't exist when it actually exists. Deleting elements from filter is not possible because, if we delete a single element by clearing bits at indices generated by k-hash functions, it might cause deletion of few other elements. Example, if we delete geeks, in given example below, by clearing bit at 1, 4, and 7, we might end up deleting nerd also because bit at index 4 becomes 0 and Bloom filter claims that nerd is not present. Working of Bloom filter. A empty Bloom filter is a bit array of m bits, all set to 0, like this. We need k number of hash functions to calculate the hashes for a given input. When we want to add an item in the filter, the bits at k indices h1, x, h2, x, hk, x, are set, where indices are calculated using hash functions. Example, suppose we want to enter geeks in the filter, we are using 3 hash functions in a bit array of length 10, all set to 0 initially. First we'll calculate the hashes as follows. h1, geeks, %10 equals 1 h2, geeks, %10 equals 4 h3, geeks, %10 equals 7. Note, these outputs are random for explanation only. Now we will set the bits at indices 1, 4, and 7 to 1. Again we want to enter nerd, similarly, we'll calculate hashes. h1, nerd, %10 set the bits at indices 3, 5, and 4 to 1. Now if we want to check geeks is present in filter or not, we'll do the same process but this time in reverse order. We calculate respective hashes using h1, h2, and h3 and check if all these indices are set to 1 in the bit array. If all the bits are set, then we can say that geeks is probably present. If any of the bit at these indices are 0, then geeks is definitely not present. False positive in Bloom filters. The question is why we said, probably present, why this uncertainty? Let's understand this with an example. Suppose we want to check whether cat is present or not. We'll calculate hashes using h1, h2, and h3. h1, cat. If we check the bit array, bits at these indices are set to 1, but we know that cat was never added to the filter. Bit at index 1 and 7 was set when we added geeks and bit 3 was set we added nerd. So, because bits at calculated indices are already set by some other item, Bloom filter erroneously claims that cat is present and generating a false positive result. Depending on the application, it could be huge downside or relatively okay. We can control the probability of getting a false positive by controlling the size of the Bloom filter. More space means fewer false positives. If we want to decrease probability of false positive result, we have to use more number of hash functions and larger bit array. This would add latency in addition to the item and checking membership. Operations that a Bloom filter supports. Insert, x, to insert an element in the Bloom filter. Lookup, x, to check whether an element is already present in Bloom filter with a positive false probability. Note, we cannot delete an element in Bloom filter. Probability of false positivity, let m be the size of bit array. K be the number of hash functions and n be the number of expected elements to be inserted in the filter, then the probability of false positive p can be calculated as size of bit array. If expected number of elements n is known and desired false positive probability is p, then the size of bit array m can be calculated as optimum number of hash functions. The number of hash functions k must be a positive integer. If m is size of bit array and n is number of elements to be inserted, then k can be calculated as space efficiency. If we want to store large list of items in a set for purpose of set membership, we can store it in hash map, tries or simple array or linked list. All these methods require storing item itself, which is not very memory efficient. For example, if we want to store geeks in hash map, we have to store actual string geeks as a key value pair, some key, geeks. Bloom filters do not store the data item at all. As we have seen, they use bit array which allow hash collision. Without hash collision, it would not be compact. Choice of hash function. The hash function used in Bloom filters should be independent and uniformly distributed. They should be fast as possible. Fast simple non-cryptographic hashes which are independent enough include Murmur, FNV series of hash functions and Jenkins hashes. Generating hash is major operation in Bloom filters. Cryptographic hash functions provide stability and guarantee but are expensive in calculation. With increase in number of hash functions k, Bloom filter becomes slow. Although non-cryptographic hash functions do not provide guarantee but provide major performance improvement. Basic implementation of Bloom filter class in Python 3. Save it as bloomfilter.py. Python. Hashtag Python 3 program to build Bloom filter hashtag Applications of Bloom filters. Medium uses Bloom filters for recommending posts to users by filtering posts which have been seen by user. Quora implemented a shared Bloom filter in the feed backend to filter out stories that people have seen before. The Google Chrome web browser used to use a Bloom filter to identify malicious URLs. Google Bigtable, Apache HBase, and Apache Cassandra, and PostgreSQL use Bloom filters to reduce the disk lookups for non-existent rows or columns. References. This article is contributed by Atul Kumar and improved by Manoj Kumar. If you Bloom filter. A Bloom filter is a space-efficient probabilistic data structure, conceived by Burton Howard Bloom in 1970, that is used to test whether an element is a member of a set. False positive matches are possible, but false negatives are not. In other words, a query returns either possibly in set or definitely not in set. Elements can be added to the set, but not removed, though this can be addressed with the counting Bloom filter variant. The more items added, the larger the probability of false positives. Bloom proposed the technique for applications where the amount of source data would require an impractically large amount of memory if conventional error-free hashing techniques were applied. He gave the example of a hyphenation algorithm for a dictionary of 500,000 words, out of which 90% follow simple hyphenation rules, but the remaining 10% require expensive disk accesses to retrieve specific hyphenation patterns. With sufficient core memory, an error-free hash could be used to eliminate all unnecessary disk accesses. On the other hand, with limited core memory, Bloom's technique uses a smaller hash area but still eliminates most unnecessary accesses. For example, a hash area only 15% of the size needed by an ideal error-free hash still eliminates 85% of the disk accesses. More generally, fewer than 10 bits per element are required for a 1% false positive probability, independent of the size or number of elements in the set. Algorithm description edit. An empty Bloom filter is a bit array of m bits, all set to 0. There must also be k different hash functions defined, each of which maps or hashes some set element to one of the m array positions, generating a uniform random distribution. Typically, k is a small constant which depends on the desired false error rate epsilon, while m is proportional to k and the number of elements to be added. To add an element, feed it to each of the k hash functions to get k array positions. Set the bits at all these positions to 1. To query for an element, test whether it is in the set, feed it to each of the k-hash functions to get k-array positions. If any of the bits at these positions is 0, the element is definitely not in the set. If it were, then all the bits would have been set to 1 when it was inserted. If all are 1, then either the element is in the set, or the bits have by chance been set to 1 during the insertion of other elements, resulting in a false positive. In a simple Bloom filter, there is no way to distinguish between the two cases, but more advanced techniques can address this problem. The requirement of designing k different independent hash functions can be prohibitive for large k. For a good hash function with a wide output, there should be little if any correlation between different bit fields of such a hash. So this type of hash can be used to generate multiple different hash functions by slicing its output into multiple bit fields. Alternatively, one can pass k different initial values, such as 0, 1, k1, to a hash function that takes an initial value, or add, or append, these values to the key. For larger m and / or k, independence among the hash functions can be relaxed with negligible increase in false positive rate. Specifically, Dillinger and Manolios, 2004b, show the effectiveness of deriving the k indices using enhanced double hashing and triple hashing. Variants of double hashing that are effectively simple random number generators seeded with the 2 or 3 hash values. Removing an element from this simple Bloom filter is impossible because there is no way to tell which of the k bits it maps to should be cleared. Although setting any one of those k bits to 0 suffices to remove the element, it would also remove any other elements that happen to map onto that bit. Since the simple algorithm provides no way to determine whether any other elements have been added that affect the bits for the element to be removed, clearing any of the bits would introduce the possibility of false negatives. One-time removal of an element from a Bloom filter can be simulated by having a second Bloom filter that contains items that have been removed. However, false positives in the second filter become false negatives in the composite filter, which may be undesirable. In this approach, re-adding a previously removed item is not possible, as one would have to remove it from the removed filter. It is often the case that all the keys are available but are expensive to enumerate, for example, requiring many disk reads. When the false positive rate gets too high, the filter can be regenerated. This should be a relatively rare event. Space and time advantages edit. While risking false positives, Bloom filters have a substantial space advantage over other data structures for representing sets, such as self-balancing binary search trees, tries, hash tables, or simple arrays or linked lists of the entries. Most of these require storing at least the data items themselves, which can require anywhere from a small number of bits, for small integers, to an arbitrary number of bits. Such as for strings, tries are an exception since they can share storage between elements with equal prefixes. However, Bloom filters do not store the data items at all, and a separate solution must be provided for the actual storage. Linked structures incur an additional linear space overhead for pointers. A Bloom filter with a 1% error and an optimal value of k, in contrast, requires only about 9.6 bits per element, regardless of the size of the elements. This advantage comes partly from its compactness, inherited from arrays, and partly from its probabilistic nature. The 1% false positive rate can be reduced by a factor of 10 by adding only about 4.8 bits per element. However, if the number of potential values is small and many of them can be in the set, the Bloom filter is easily surpassed by the deterministic bit array, which requires only 1 bit for each potential element. Hash tables gain a space and time advantage if they begin ignoring collisions and store only whether each bucket contains an entry. In this case, they have effectively become Bloom filters with k equals 1. Bloom filters also have the unusual property that the time needed either to add items or to check whether an item is in the set is a fixed constant, k, completely independent of the number of items already in the set. No other constant space set data structure has this property, but the average access time of sparse hash tables can make them faster in practice than some Bloom filters. In a hardware implementation, however, the Bloom filter shines because its k lookups are independent and can be parallelized. To understand its space efficiency, it is instructive to compare the general Bloom filter with its special case when k equals 1. If k equals 1, then in order to keep the false positive rate sufficiently low, a small fraction of bits should be set, which means the array must be very large and contain long runs of zeros. The information content of the array relative to its size is low. The generalized Bloom filter, k greater than 1, allows many more bits to be set while still maintaining a low false positive rate, if the parameters, k and m, are chosen well. About half of the bits will be set, and these will be apparently random, minimizing redundancy and maximizing information content. Probability of false positives edit. Assume that a hash function selects each array position with equal probability. If m is the number of bits in the array, the probability that a certain bit is not set to 1 by a certain hash function during the insertion of an element is 1 If k is the number of hash functions and each has no significant correlation between each other, then the probability that the bit is not set to 1 by any of the hash functions is 1 k. We can use the well-known identity for e. Lim m rightward arrow infinity, 1 m, to conclude that, for large m, 1 m, k equals 1 m, k slash. If we have inserted n elements, the probability that a certain bit is still, the probability that it is 1 is therefore. Now test membership of an element that is not in the set. Each of the k array positions computed by the hash functions is 1 with the probability as above. The probability of all of them being 1, which would cause the algorithm to erroneously claim that the element is in the set, is often given as. This is not strictly correct as it assumes independence for the probabilities of each bit being set. However, assuming it is a close approximation, we have that the probability of false positives decreases as m, the number of bits in the array, increases, and increases as n, the number of inserted elements, increases. The true probability of a false positive, without assuming independence, is where the braces denote Stirling numbers of the second kind. An alternative analysis arriving at the same approximation without the assumption of independence is given by Mitzenmacher and Upfall. After all n items have been added to the Bloom filter, let q be the fraction of the m bits that are set to 0. That is, the number of bits still set to 0 is qm. Then, when testing membership of an element not in the set, for the array position given by any of the k hash functions, the probability that the bit is found set to 1 is 1q. So the probability that all k hash functions find their bit set to 1 is 1q, k. Further, the expected value of q is the probability that a given array position is left untouched by each of the k hash functions for each of the n items, which is, as above. EQ equals 1 m, kn. It is possible to prove, without the independence assumption, that q is very strongly concentrated around its expected value. In particular, from the Azuma-Hefting inequality. Because of this, we can say that the exact probability of false positives is optimal number of hash functions edit. The number of hash functions, k, must be a positive integer. Putting this constraint aside, for a given m and n, the value of k that minimizes the false positive, the required number of bits, m, given n, the number of inserted elements, and a desired false positive probability epsilon, and assuming the optimal value of k is used, can be computed by substituting the optimal value of k in the probability expression above. Epsilon equals 1e, mn ln2, nm, mn ln2. Which can be simplified to ln epsilon equals mn, ln2, 2. This results in m equals n ln epsilon, ln2, 2. So the optimal number of bits per element is mn equals log 2 epsilon ln2 1.44 log 2 epsilon. With the corresponding number of hash functions k, ignoring integrality. K equals ln epsilon ln2 equals log 2 epsilon. This means that for a given false positive probability epsilon, the length of a Bloom filter m is proportionate to the number of elements being filtered n, and the required number of hash functions only depends on the target false positive probability epsilon. The formula Bloom filter, a probabilistic data structure. Bloom filter is a probabilistic data structure invented by Burton Howard Bloom in 1970. It allows for membership check in constant space and time. Bloom filter trades exactness for efficiency and has a large number of applications in software engineering. Some of the properties of Bloom filters are: it allows for membership lookups in constant space and time. Bloom filter can very quickly answer yes/no questions, like, is this item in the set? Very infrequently it will give a false positive answer, implies it will say yes if the answer is no, probably in the set. It will never give false negative answer, implies it will never say no if the answer is yes, definitely not in the set. Basic Bloom filter supports two operations: test and add. It has constant time complexity for both adding items and asking whether a key is present or not. You can't remove an item from a Bloom filter. It also requires very less space compared to the number of items you need to store and check. Bloom filters uses hash functions, and before discussing Bloom filter in detail, let's have a look at hashing and hash functions. Hashing and hash functions. A hash is like a fingerprint of your data. A hash function takes input data which can be of any length and gives back output as an identifier of smaller, fixed length. The identifier can be used to index or compare or identify data. Most hash functions are one-way operations, which means you can get an identifier from the data, not vice versa. Two-way hash functions also exist, but they are not particularly useful. Important properties of hash functions are: same input must always have the same output. It is one of the most important features. The output values should be uniformly distributed. It means each possible output value should be equally likely. The output should be distributed randomly. Similar input should not give similar output. Each input should give a unique output to minimize the number of collisions. It should be fast. Different hash functions are designed for different tasks. Their properties differ based on the task for which you are using them. Hash functions used with Bloom filter should have the following properties. It should be fast. The hash function should have rare collisions and hash value should be evenly and randomly distributed. Bloom filter implementation. A basic Bloom filter will have two operations: test and add. Base data structure for Bloom filter is bit vector or bit array. It uses a bit array of size m and k hash functions. Initially, all the bits in bit vector will be set to 0. To add an element to the Bloom filter, we hash the element k times using hash functions and set bits at indexes of those hash values. To test for membership, we simply hash the element with hash functions and then check if those indexes are set in the bit vector. If the bit at all those indexes is not set, you know that the element is not in the set. If they are set, it might be because the same element or combination of other elements could have set the same bits. Later is the reason why Bloom filter can sometimes give a false positive answer. For illustration, we will use a bit array of size 10 and 3 hash functions. Initially, all the index in the bit vector will be 0. Let's add system to the Bloom filter. Hash values for 3 hash functions are 4, 5, and 9. We set the bits at those indexes to 1. Let's add design to the Bloom filter. Hash values for 3 hash functions are 0, 1, and 3. We set values at these indexes to 1. Now let's check whether Bloom filter has system. System will be hashed to 4, 5, and 9. All 3 bits are set in the Bloom filter, so we can say that system exists. False negative is impossible, definitely not in the set. Let's check membership for blog, which hashes to 6, 7, and 9. In Bloom filter, only index 9 is set, 6 and 7 are not. This means the blog is not present in the Bloom filter. If it was present in the set, index 6 and 7 would have been also set. So when an element is not present in the set, we are definitely sure that item is not present and there is no scope for false negative. False positive, possibly in the set. Now let's look at the case of false positive. We want to check membership for interview, which hashes to 3, 5, and 9. We can see 3, 5, and 9 are set to 1, which means interview is present. But wait for a second, we never added interview to the Bloom filter. This is a false positive. Those indexes were set by system and design. More occupied cells in the bit vector, higher the chance of false positive. Remove an item. Suppose we have already added interview to the Bloom filter. Now we want to remove system from the Bloom filter. To do that, we need to unset indexes 4, 5, and 9. If we do so, interview will also be removed from the Bloom filter because 5 and 9 were also set by interview. It is almost impossible to remove an element from a Bloom filter without removing other elements. Bloom filter size and number of hash function. Bit array size and number of hash functions plays an important role in the false positive rate for the Bloom filter. If the size of the bit array is too small, all bits will be set to 1 more quickly. It will start giving a false positive result for every input after that. Larger the bit array, lower the false positive result. If we have too few hash functions, there is more chance for a false positive result. If we have too many hash functions, Bloom filter will become slow because it will have to hash every input that many times. If there are k number of hash functions, test operation will be O, k. Suppose n is the number of elements, m is the size of the bit array, is the number of hash functions, p is the false positive rate. Source, https://www. As we can see from the above graph that with increasing value of the number of hash functions k, will reduce false positive rate. But a large value of k can also make our Bloom filter slow. In this case, n equals 10 m and p. For more information on this calculation, please refer to this blog by Abhishek Bhatt. Applications. Bloom filter has a large number of applications in software engineering. Medium uses Bloom filter in Medium blog recommendation to check whether a user has already read this post before or not. Read more about it on this amazing blog. Google Bigtable, Apache HBase, and Apache Cassandra, and PostgreSQL use Bloom filters to reduce the disk lookups for non-existent rows or columns. Avoiding costly disk lookups considerably increases the performance of a database query operation. Bloom filter is used by content delivery network provider Akamai to avoid caching web objects which are requested by users just once, also known as one-hit wonders. Using a Bloom filter to detect the second request for a web object and caching that object only on its second request prevents one-hit wonders from entering the disk cache, significantly reducing disk workload and increasing disk cache hit rates. The Google Chrome web browser used to use a Bloom filter to identify malicious URLs. Any URL was first checked against a local Bloom filter, and only if the Bloom filter returned a positive result was a full check of the URL performed, and the user warned if that too returned a positive result. Some of the existing implementations of Bloom filters are: Bloomd is a high-performance C server which is used to expose Bloom filters and operations over them to networked clients. It nicely fits into the microservices architecture. PyreBloom is Python-based implementation of Bloom filter based on Redis. The Cuckoo filter is another variation of the Bloom filter. Cuckoo filters support adding and removing items dynamically while achieving even higher performance than Bloom filters. There is a nice blog by Farhan on the difference between Cuckoo and Bloom filters. What are Bloom filters? A tale of code, dinner, and a favor with unexpected consequences. Genesis. So how do you know whether someone's read a post already? Asks Sarah, Medium's legal counsel. We're at dinner for my birthday, yet somehow have gotten onto the topic of work yet again. Sarah is referring to Medium's personalized reading list, a recommendation system that I helped build, which suggested new and interesting posts to users when they visited Medium's homepage. I sigh. I'm hungry and the main course has just arrived, venison glazed in honey, served with a sweet potato hash. The problem is, I find describing technical solutions like this really interesting, and Sarah knows it. If she wasn't vegetarian, I'd suspect it was a ploy to distract me so she could get her hands on my dinner. My wife shakes her head with a rueful smile and turns to chat to another friend. I put my fork down, and begin to explain to her all about the Bloom filter, an ingenious data structure invented 50 years ago, and how we use it at Medium to answer Sarah's question. Most of the rest of the dinner table ignores us, and no one bats an eyelid when I begin drawing on napkins to illustrate the concept. All of this has happened before and all of it will happen again. I pause for a second, and look up. And what does monkey hash to? I ask Brad, a median sitting across from me at the dinner table. Monkeys hash to 10, 2, and 1, he says promptly, and I nod approvingly. Sarah is nonplussed. 2 years ago, before Sarah joined, I gave a short presentation on Bloom filters to Medium's then 25 staff. I'm impressed Brad remembers this made-up fact about a made-up hash function, which was made up to illustrate the possibility of false positives. But more on that later. Hashing. To understand Bloom filters, you first have to understand hashing. To understand hashing, you don't have to understand maths, which is good, because I'm a middling mathematician at best. I sit at the median, maybe. A hash is like a fingerprint for data. A hash function takes your data, which can be any length, as an input, and gives you back an identifier of a smaller, usually, fixed, length, which you can use to index or compare or identify the data. This is a hash of my full name. B3F9B3A3504. Most hash functions are one-way operations, which is to say you can figure out an identifier from the data, but you typically can't do the reverse. You couldn't look at that hash above, for example, and know that my full name is James Graham Michael Swanson Talbot. Reversible hash functions do exist, but they tend to be pretty trivial, and not particularly useful. There are a few properties which are desirable in a useful hash function. The most important one is that the same input must always hash to the same output. Really, that's the defining feature. If the same input gave you a different output each time, it wouldn't be very useful as an identifier. Ideally, the output values should be distributed uniformly, that is, each possible output should be equally likely. For a lot of use cases it is also important that the outputs be distributed randomly, similar inputs should not give similar outputs. For some use cases, usually in security, it is also important to minimize collisions, meaning, as far as possible, each input should give a unique output. Finally, in most cases, though not always, you want it to be fast. No one wants to wait for anything these days, and that includes programmers. The combination of hash function properties that you care about will vary wildly depending on the task for which you are using them. And hash functions are used in a lot of tasks. Shazam uses hashes to figure out what song you are listening to. If you need to find duplicates in a set of things, you might use a hash. Databases? Giant hashes. This post on Medium was delivered to you securely. You can probably see a green padlock on the browser address bar that confirms this. Hashes are important in that process too. You may even have heard of some of these algorithms. SHA-1, secure hash algorithm, was devised by the NSA, and for a long time was used to secure lots of internet communication. MD5 is another popular one, often used to prove that the
I think I need to study more hash functions. Maybe I should do a part on blockchain for cryptography and study that. I think that's a good idea. This is essential component, I think, for blockchain and everything else. I was thinking about as I was reading this, that the cryptography is kind of like a boundary between computation. It goes back to the NP completeness thing, where everything is built on top of this assumption of irreversibility from hash functions. So hash functions are probably at the boundaries of what we think computation can do, which is an interesting thing to think about.
MD5 is another popular one, often used to prove that the file you're downloading is the one you think it is, and not some malware written by the NSA to infect your computer and spy on you. In fact, MD5 was the hash function I used to encode my name further up the page. Some hash functions have exotic and nonsensical names. This is computing after all, and so you also get things like city hash, murmur hash, and spooky hash. There are literally thousands of named hashing functions. Some are secure, but comparatively slow to calculate. Some are very fast, but have more collisions. Some are close to perfectly uniformly distributed, but very hard to implement. You get the idea. If there's one rule in programming, it's this: there will always be trade-offs. While you don't have to be a genius to understand hashes, you do have to be a pretty exceptional mathematician or computer scientist to create one, or at least one that's useful. Take this elegant, impenetrable piece of code by Paul Hussey, for example, which he calls superfast hash, excluding some helper code. UN32T superfast hash, const char. This is a series of fast operations that do things.
I think I'm gonna search for, if I have time after this one, I'm gonna search for the one I was thinking about, explaining Bloom filters in the context of blockchain.
This is a series of fast operations that do things like addition and multiplication, inverting of ones and zeros, munging, and
It's obviously not hard to understand at all. I think I already get the concept and how it works, but I want to remember the article from the blockchain context. Probably not going to change much here as well. Just see if everything is correct, which it probably is.
This is a series of fast operations that do things like addition and multiplication, inverting of ones and zeros, munging, and melding parts of the data with itself, shifting bits this way and that. And at the end of it, you get an almost perfectly unique fingerprint of the input data. Why pick those operations, with those numbers, in that order? Beats me. Paul C. might not be a wizard, but I've seen no evidence of that. What matters is, we have a way of taking any data, like the contents of a YouTube video, or an MP3 file, or the word monkey, and getting back a fingerprint that is predictable in length and unique, mostly, to that item. A quick favor. This is all Marcine's fault, really. Marcine, if you didn't know already, is obsessed with typography. This admirable trait makes him an easy mark if you need any tasks doing that involve mediums fonts, or icons, which are also a font. Sometime last year, I was working on a feature which required a new icon. I was keen to get it deployed to the world before the weekend deadline, so I sent him a quick message at 6 p.m. Any chance you can get a new icon into our font sometime tomorrow? I want to ship feature X. And what will you do for me? He asks, seemingly nonchalantly. Now, recounting this exchange to you, I instead picture him rubbing his hands together in gleeful expectation like Mr. Burns. Will you fix a bug of my choosing? I kind of have a full day tomorrow. Sure, I say, glad that we're going to be able to ship the feature. Anything you like, I promise, naively. 6:30 p.m. Slack pings with a notification. PR is in, he writes, announcing to me that he's already completed the work. I want you to fix this. This. The word this is interesting for JavaScript programmers, a source of confusion for newcomers to the language, and frustrating even to Journey people who periodically forget about the language's idiosyncratic functional scope. The gist of it is, whenever you see this in JavaScript code, you never quite know what it's referring to. For programmers who are used to everything being in its proper place, this can be disconcerting. JavaScript is full of these objectionable, endearing nuances, and is possessed of a flexibility bordering on pathological. Picture a politician conversing with the lobbyist whose large donation made their election possible. JavaScript is more flexible than that. Medium's server-side codebase is primarily written in JavaScript, and the personalized reading list recommendation system abused JavaScript's aforementioned flexibility with gusto. We discovered later that its correct performance relied, unintentionally, on a particular quirk in how asynchronous instructions were chosen for processing. It was a wonder that it worked at all. Looking back at that code, well, let's just say, nobody's a worse programmer than your past self. Like hashes, recommendation systems are all around us. Netflix is a recommendation system. StumbleUpon and Pandora are too. Amazon's, because you bought Cryptonomicon on Kindle, feature. Facebook's, people you may know, their stream, their search results. All recommendation systems. And the tragedy of recommendation systems is that people only notice them when they're broken. Very few people say, I love Netflix's suggestions. Many more say, ugh, Pandora played me the exact same thing yesterday. Recommendation systems are the sports referees of the computing world. To give good suggestions, you need to collect data about your users and find interesting ways to use it. For Medium, a simple method for suggesting a story might be, because you follow the author. A more complex one might be collaborative filtering, which you can describe as, people who recommended lots of the stories that you recommended also recommended this story. A typical recommendation system will take a bunch of these methods that make good guesses about what you like, combine their results together so you get a varied selection, then sort them so the ones with the highest score come first. It should do this very quickly. And woe betide the system that shows someone the same thing too many times, for that way lies frustration, anger, and lots of all caps emails to user support. Medium users have written hundreds of thousands of posts. Each one of these has an ID and is stored in a database table, but the table is so big, and accessed so frequently, that it can't fit on one machine. When you ask the database for a specific post, how does it know where to find it? A hash function. The database takes the ID, hashes it to a unique value, and uses that to jump straight to the record location, just like you'd use the index of a book to jump straight to a specific page number. Back when the books Amazon suggested to you were on paper and had indices. When suggesting stories to a user, the system may come up with thousands of possibilities, but not every one will be appropriate for a user. Perhaps a story has been suggested to them too many times already. Perhaps they've already read it. We need to filter those stories out, but we don't want to retrieve thousands of records from the database to do it. We need a mechanism that is particularly good at answering the question, has this been seen before? And for that, we use a Bloom filter. Returning the favor. Unfortunately for me, the this that Marcine is talking about is a bug that I can't help him with. He wants me to change the ordering of how people appear in a particular list, so that your friends appear first. It's not a complex change, but the way we store our data means the list will become slow to load, and infinite scrolling will break. We are sadly stuck with what we have until we restructure our data storage, which, given our other priorities, isn't likely to happen soon. Trade-offs happen in product development too. I report back sheepishly to him that he will have to choose something else. The Christmas break rolls around, and I forget all about my promise. And then on February 18th, this appears on Slack. Mwickery 9:08 AM BTW. I was supposed to send an elephant never forgets, nor either, apparently, do Polish designers. Incredibly, the bug he sends me this time is literally impossible to fix. Partly out of guilt, but mostly because he's a fantastic conversationalist, I invite him to my birthday dinner in June. And then, a week or so ago, this. Mwickery 1:24 PM. This, Paul Ford, in case you didn't know, recently wrote an incredible treatise on programming and all that surrounds it. Funny, accessible, informative, and time and space. The world hardly needs another definition of the word algorithm, but here I go anyway. An algorithm is a set of steps to solve a problem. Simples. Algorithms don't really have anything to do with computers, although computers turn out to be very handy algorithm processing machines.
God damn. It's just a bunch of different things that are not related at all to
In Bloom,
the thing.
Burton Howard Bloom, the eponymous hero of our tale, and, it has to be said, possessed of a name with a very pleasing cadence, Burton Howard Bloom, studied computer science at MIT from 1963 to 1965. He invented the data structure that came to be known as the Bloom filter in 1970 while working at Computer Usage Company in Newton Upper Falls, MA. Bloom filters can very quickly answer variations on the yes/no question, is this item in the set, like, have I seen this item before? There are two important caveats though. Very rarely, it will say yes when the answer is actually no, although it will never say no when the answer is actually yes. You also can't remove an item from a Bloom filter. Like elephants and unrelenting Polish designers, Bloom filters never forget. If you can accept a couple of false positives from time to time though, and if you don't need to remove items, it's a great choice. A Bloom filter has constant time complexity for both adding items and asking whether they are present, which makes it doubly groovy, and it requires very little space relative to the size of the items you need to store and check. It gets these properties in large part because it is based on hash functions. For the hash functions that Bloom filters use, collisions in the outputs don't really matter too much, as long as they're reasonably rare. It's more important for the outputs to be evenly and randomly distributed. And, of course, we want our hash functions to be fast. You can think of a Bloom filter as a large set of numbered buckets, each one starting off empty. Let's imagine we want to keep track of the pets that Ev Williams owns. To do this, we're going to use a Bloom filter with 10 buckets and 3 hash functions. We start by putting cat into our Bloom filter. Internally, the filter takes cat and passes it to the 3 hash functions, which return 3 identifiers. In this case, cat hashes to identifiers 3, 4, and 10. The filter goes and fills up every bucket whose number matches one of the identifiers, 3, 4, and 10. It's able to do this very quickly because it can jump straight to each bucket to fill it up, just like you jump straight to page numbers from an index. Next we put dog into our filter. Using the same hash functions, dog hashes to 5, 2, and 1, so those buckets get filled up too. After we've done both of these operations, buckets 1, 2, 3, 4, 5, and 10 are full. Does Ev have a cat? We can ask the filter.
Once you get to the blockchain stuff, you write the articles, the consensus. But the reason why I'm gonna do all of the other articles first is because I'm not sure until when I'm gonna have access to ChatGPT. So I want to finish all of the other ones first. And there's a lot of them to finish. But after I finish all of this, I'm not really sure how long it's gonna take, to be honest, because it's gonna be really hard, I think. Writing the articles, I think I can write most of them today, probably using ChatGPT, because it's just do the right prompts and then get the information. But to review them is gonna be very hard. But hopefully I can finish them fast. Or maybe I'll stop at. I think I'll do trees first, then maybe tries because it's related to the blockchain. But maybe I will stop before because I have this book here that I wanna read. It's about Ethereum, and then I wanna move on more to stuff focused on the blockchain instead of the algorithms, because I think they're more relevant to what I'm trying to do now, which is to find a job in the blockchain. So I'm not really sure what to do. I'm probably gonna do, depending on how hard it is to do all of this stuff here, I'm gonna do blockchain first. I didn't like this article that much, to be honest. It's just a bunch of filler stuff that has nothing to do with Bloom filters. But the concept is really easy. It's similar to a hash table, but then you store in the space of binaries the hashes, and then based on the hashes you can see whether or not you have the thing on the set. And then there's the chance of false positive, because if you add different words, there can be hash collision, and that depends on the size of the set, which is the size of the Bloom filter. So the higher the size of the Bloom filter, the slower it is, but then less chance of hash collision, and vice versa.
Eth goes Bloom, filling up Ethereum's Bloom filters. We spent some time at the IC3 Ethereum bootcamp hacking on Ethereum's Bloom filters. This article
Now or more just reading this stuff. I'm probably gonna see if I'm gonna rewrite any of this off stream, which I think I'm not really gonna do. I'm just gonna check to see if there's any misinformation here or anything that is wrong, but I'm gonna leave it like this because I don't care that much about it. As long as it's correct, it doesn't really matter. So yeah, I I think most of these algorithms most of these articles I'm just putting to have like a decent amount of content on the site. And some of them I care about because they're related to stuff that I'm trying to do now, but most of them I don't really give a shit about. It's more just to cover the topics. And that's why, and it feels like one of them, like this is important to know because of the blockchain is related. But the article itself, I think, is not that, doesn't matter that much. As long as it's accurate. I want to study more the cryptography part and also the code that is involved with the cryptography, because I think that's the hardest part to understand, even in Ethereum, and is the part that gives you the most power, let's say, to build your own things, because everything is based on the cryptography, and obviously it's probably really hard. Zero knowledge proofs and KGZ or KZG commitments. I think it's KZG. That kind of stuff.
This article goes over the result of that work, and some of the interesting things we learned. The code used for these experiments is available on GitHub here. Quick FYI, this article assumes you know a little bit about bit arrays, hash functions, and Ethereum. Bloom filters. Let's first explain what Bloom filters actually do. A Bloom filter is a probabilistic, space-efficient data structure used for fast checks of set membership. That probably doesn't mean much to you yet, and so let's explore how Bloom filters might be used. Imagine that we have some large set of data, and we want to be able to quickly test if some element is currently in that set. The naive way of checking might be to query the set to see if our element is in there. That's probably fine if our data set is relatively small. Unfortunately, if our data set is really big, this search might take a while. Luckily, we have tricks to speed things up. A Bloom filter is one of these tricks. The basic idea behind the Bloom filter is to hash each new element that goes into the dataset, take certain bits from this hash, and then use those bits to fill in parts of a fixed-size bit array, e.g. set certain bits to 1. This bit array is called a Bloom filter. Later, when we want to check if an element is in the set, we simply hash the element and check that the right bits are 1 in the Bloom filter. If at least one of the bits is 0, then the element definitely isn't in our dataset. If all of the bits are 1, then the element might be in the dataset, but we need to actually query the database to be sure. So we might have false positives, but we'll never have false negatives. This can greatly reduce the number of database queries we have to make. Bloom filters in Ethereum. Bloom filters are used in Ethereum to minimize the number of block queries that clients need to make. Imagine you want to find every time you've transferred some token X. The naive way of searching for this information would be looking through every past historical transaction. This would take a very long time. Luckily, the ERC-20 standard requires that contracts fire off an event, or log, whenever tokens are transferred. These events are then stored in a Bloom filter that is part of each block. From here, finding all your token transfers becomes much easier. You can first take the event of interest, hash it, and figure out which bits to look at in the block level Bloom filters. If any of these bits are set to 0, then the event must not have been generated in any transaction in this block. If all of the bits are 1s, then you can check the rest of the block for possible transactions. Blooming the blooms. At the IC3 Ethereum bootcamp this summer, we realized it might be possible to completely fill up the block level Bloom filter. Remember that certain bits of a Bloom filter are set to 1 based on the hash of the elements that go into the filter. If we can carefully pick which elements to insert, we could set every bit in the Bloom filter set to 1. The Ethereum Bloom filter implementation is currently 2048 bits and sets 3 bits in the filter based on the first few bits of the hash of the item. This means we can fill the entire filter by generating only 683, seal of 2048/3, events. A smart contract can generate as many events as it wants, so this can definitely work. The next challenge was figuring out how to make this as efficient as possible. We first thought we might have to create a smart contract with a bunch of different events and fire off all of those events in a single function call. Unfortunately, that would have made deploying the contract prohibitively expensive. Then we looked into how Solidity events actually work under the hood. They actually just execute a logx instruction. We realized that it wasn't even necessary to actually define any events and trigger them manually, we could just log a bunch of junk. The whole contract took up only a few lines of code. Next up was figuring out what data to put in each log to fill the Bloom filter correctly. This basically just required grinding out 3-byte values, hashing them, checking what bits they would flip in the filter, and throwing out any pre-images that overlapped with something else. 682 events get us to 2046 bits, so the last event will necessarily overlap with at least one other bit. Searching for the right input data gets exponentially more difficult as you get closer and closer to the full filter. Our laptops could only complete the search after 10 to 20 minutes, so we cheated a little and lowered the overlap requirement for the last few events. This trick resulted in a huge speedup, mining the required data in 10 to 20 seconds, at the cost of only 10 more events. LOGX instructions cost 375 gas per instruction, plus 8 gas per byte of topic data. Call data is another 68 gas per byte. With the base transaction fee of 21,000 gas, we're looking at a theoretical limit of a little over 330,000 gas to fill the whole block. Our method usually lands at about 515,000 gas, so we're far from the maximal limit, probably because of loop overhead. So what? A full Bloom filter is really annoying for Ethereum clients. Anyone who wants to check for the presence of some event in a block would have a 100% false positive rate, which triggers a database query. Database queries are slow, so this could theoretically have a performance impact on the network. At the very least, a full Bloom filter is a useless Bloom filter, and it's an extra 2048, pointless, bits that need to be transmitted along with each block. A bloomed Bloom is a set 1. Fortunately, this attack isn't cheap. At current gas prices, you'd need to spend 20 cents, 30 cents per block, every block, to keep filters full. We've explored some client code and determined that the impact is probably quite low, but it seemed useful to explore. Mitigations. There are a few ways to mitigate this attack. The EVM could simply charge a little more for the logx instruction to make up for the potential database query. We could also agree to use a larger Bloom filter to, linearly, increase the cost to attack. However, this solution would also up the Ethereum block size. Or we could just ignore this entirely, for now. It doesn't seem like breaking behavior right now, though that might change in the future. It's definitely something to keep an eye on. People have been talking about Ethereum's Bloom filters a little bit recently, so maybe we'll start to see more conversation. Bloom filters. Millions of people search the internet, government databases, private databases, and blockchains every day for medical advice, financial updates, weather reports, maps, and more. Likewise, millions of people want or need fast searches. An effective method to speed up many searches is the use of indexes. Indexes, like those at back of textbooks, provide the locations of all search terms. A possible drawback is that they require large amounts of storage. An effective method to speed up many searches, with less storage requirements, is the use of Bloom filters. These are important in many areas such as mobile and embedded devices. Bloom filters are binary strings used to quickly determine set membership with nominal storage requirements. Browsers use them to detect malicious websites. Databases use them to avoid searching for non-existent data. Bloom filters require less memory than indexes, but they sometimes give false positives. In other words, they might claim an object is a member of a set when it is not. It is noteworthy that Bloom filters never give false negatives. They never claim an object is not in a set when it actually is. Browser Bloom filters might incorrectly claim safe websites are malicious, but they will never claim malicious websites are safe. Fortunately, extra checks can always be performed to eliminate any false positives. To build a Bloom filter for the set x, x2, x3, x subscript n, with hash function h, calculate h, x, x2, h, x3, h, x subscript n. Is the bitwise or operator. H is only valid if the number of set bits, ones, in all hashes is always less than or equal to some selected maximum. Larger Bloom filters have less false positives. Bloom filters of several megabytes are not uncommon. As hash functions typically do not have large enough hashes, not to mention hashes with required number of set bits, adequate hashes are often constructed from multiple hash functions. A common recipe is to have a group of hash functions each set a single bit in the construction of a valid hash. For example, to set a bit in a hash with 2 superscript 3 bits, the first 23 bits of the secure hash algorithm 1, SHA-1, hash can be used to select the position of a bit to set. To determine if an object x might be in a set with Bloom filter b, built with hash function h, determine if h, x, and b equals h, x. And is the bitwise in operator. Notice that the test only returns true if all the set bits in h, x, are also set in b. Basically, groups of set bits in b correspond to elements. X might be a member of the set if and only if its group of set bits corresponds to a group in b. The reason b can only determine if x might be in the set is because b contains the bits of several elements. Bloom filters also allow like clients to quickly and privately obtain account information without downloading the entire blockchain. Bloom filters are a powerful tool that allows additional innovation.
Let me see if this is correct or not. So I think it is correct. Probably got this stuff from Wikipedia because it's exactly this formula here. Yeah, so this is P here. Maybe I would leave it like this. I was gonna put here that it is used to store events on Ethereum in the box. But I think that like this is probably better because I'm not really sure, but I assume that other blockchains probably use bloom filters as well. This is just a more efficient way to store data about events. Yeah, I'm gonna leave like this and then I'm gonna get the implementation with ChatGPT and put there. If it works. And maybe I will stop here. Let me see how much time I have. 17 minutes. I think I'm gonna stop here, and like I said, what I'm gonna do is create the articles with ChatGPT. I wanna create as many as I can from this. I think after writing all the articles about all these algorithms and the data structures that I already have written, and some of the articles about consensus protocols, about the blockchain, I think from that point, I think I'm not gonna use ChatGPT too much anymore, because those are I think, as far as I can think, those are the main topics that I wanna. Well, actually, I would use ChatGPT, but in other ways, to write articles about the compiler in Python or interpreter, Python interpreter, and things like that. But then is more using ChatGPT for research and not for building the article itself. So that's the reason why I want to get out of the way these articles until I have access to ChatGPT, because after that point, I'm probably gonna do the articles fully on my own and just do the research for the stuff that I want to write it about. Oh, maybe actually articles about cryptography and linear algebra as well would be good to use ChatGPT. So I might do that as well. I want to do the articles that require ChatGPT first until I have access to it for free. And then once I have this amount of those articles, then I can start writing more of the stuff that I want to write about. That is going to be more unique, probably. So I'm gonna stop here. I'm gonna do this stuff off stream. I'm probably gonna come back tomorrow, or maybe today. I think, yeah, it's gonna be hard, I think, to finish all of this today. It's probably around hundreds of articles, like 150 articles, but we'll see. And then next time I'm gonna probably review the blockchain articles first, I think. I have 4 consensus algorithms articles. I'm gonna review those first, I think, tomorrow. And then after I review them, I'm gonna start reviewing those about algorithms. So yeah.